girls, children of all ages, welcome, welcome, welcome to another exciting edition of HL Chemistry Flipped Classroom. We're going to be talking about energetics today, intro to the energetics unit, topic 5 and 15, called thermochemistry or thermodynamics more commonly, but I think on the new syllabus referred to as energetics. So, without further ado, let's get right into it. This topic is one of the more difficult ones for sure in the IB syllabus. For some students, it's just a little bit hard to wrap your brain around what's going on with this. But bottom line is, two things exist in the universe. You got matter. Matter's the stuff. If you want to get a little more technical, it has mass and takes up space. And then there's also energy. And energy is the thing, rather than stuff, I should suppose. It should be the thing that can make stuff move, or energy is what gives matter the ability to do work, which is basically apply a force over a distance. And that's really about the best way we can define energy. It's just something that imbues matter or gives matter the ability to do work, to kind of move around. We're going to be talking about different kinds of energy. There is energy that's stored in chemical bonds. Those bonds have the potential to change. So there's chemical potential energy stored in bonds, which can be released when you, for instance, burn something. Heat. It turns out heat is actually a little bit to define as well, but heat is the thing, or heat is that which it's that which is transferred from a hotter body to a colder one due to temperature differences. So, if you heat up a piece of iron, you set it down in a room, the air in the room will heat up a little bit, the iron will cool down, and eventually everything will come to the same temperature. That's called thermoequilibrium. So heat energy is the type of energy that does that. It's the energy that's transferred from hotter bodies to colder ones. So here's an example. This is a red-hot 1,000-degree ball of nickel, and it's placed on a block of ice. So the nickel at first is very much hotter than the ice, and quite dramatically sinks down inside of it. So energy is going from the nickel to the ice, but eventually the ice and the nickel would reach the same temperature. Probably, not immediately, but a few minutes after this little GIF ends up stopping. So that's kind of a cool example of temperature change there. And there's all kinds of interesting things going on. There's phase changes happening, which there's all sorts of interesting stuff that happens with energy and phase changes, but we'll get to that later. So it's important to understand, some people kind of confuse heat energy with temperature, and we need to be really clear on what each one of these things is and the definition of each one of them. Temperature is a measurement. It's proportional to the average kinetic energy of the particles in a substance, how fast the particles are moving around. At a higher temperature, the particles are, on average, going to be moving around faster than at a lesser temperature. So this is called the Maxwell-Boltzmann diagram or distribution. And basically what we got here is, this would be a sample of gas. A sample of gas at two different temperatures, 300 Kelvin, 1,000 Kelvin. I'm not sure it's properly scaled and all that, but at least it would be roughly true. So at 300 Kelvin, certain molecules are going to have a certain speed, a certain velocity, a certain kinetic energy, but some of the molecules are going to be going faster, some are going to be going slower. So at the higher temperature, they have some average kinetic energy, which we're kind of calling 300 Kelvin. At the higher temperature, notice this is where the average is in the bell curve. So notice the average is shifted in this direction, so it's right about here. We'll talk about why the shape changes and all that. We're going to talk more about these later, but what's important to know now is temperature is proportional to average kinetic energy of the particles, and as you heat something up, average kinetic energy increases. But there's a wide range of temperatures. It's a bell curve like height or anything else. Okay, so there's some laws of thermodynamics. There's the first law of thermodynamics, which is in chemical processes, energy cannot be created or destroyed. It can only change forms. Now, it is possible for matter to change to energy. That's what E equals mc squared, and we will talk about that. But in chemical processes, an everyday chemical process, you cannot create or destroy energy. You can only cause it to change forms. So we'll be considering that quite a bit. And the second law of thermodynamics, in a nutshell, says that the entropy, which you can think of as the disorder of the universe, is going to be increasing over time. So the universe is getting steadily more chaotic and more disordered. Sort of like your room at home. Your room without your constant input will degenerate into a state of total disorder and total entropy. and then your parents will get mad at you. But let me say this: next time they get mad, if your room's a mess, just say, "Hey, it's the second law of thermodynamics. What do you want me to do about it?" Now that probably won't work, but you can try it. Okay, so there's no device, certainly not a thermometer, because thermometers don't measure heat energy, they measure temperature. You cannot measure energy directly, but you can track or you can study changes in energy. And because of that reason, we have to we have to take a point of view when it comes to energy. And as chemists, we're going to take the point of view of the system. The system is the process or object that you're talking about, and the surroundings is literally everything else in the universe. Now, in all practical purposes, you could probably restrict it to the room that you're in, but it would be literally everything else in the universe. So when we talk about energy changes, we're going to take the point of view of the system. And here's some units of measurement. Calorie is defined as the amount of energy needed to raise the temperature of 1 gram of water 1 degree Celsius. So when you look at the back of a nutrition label, one thing that's kind of confusing about that is they will give calories with a capital C, which is actually a kilocalorie. So if you look at a Snickers bar and it says it has 210 calories on it with a big C, that's actually 210 kilocalories, which is 210,000 of these little c calories here. That's just the way that food is defined. The calories in food are defined. But, quite literally, it's a measurement of how much heat energy is available in the Snickers bar. And one of the things they do to determine how many calories in a Snickers bar are they burn it, or maybe they at least burn the components of it. And they figure out how much it changes the temperature of water in a device called a bomb calorimeter. But we'll talk more about that kind of thing. Another energy unit, the one we're going to be using more commonly, is the joule, which is defined as the energy to move move 1 Newton 1 meter. You've done a joule's worth of work. An apple has a weight of about a Newton. So if you move an apple about a meter, you've done a joule's worth of work on it. It's a pretty tiny amount of energy. We'll often talk in kilocalories. So these are 2 units of energy that we will be discussing quite a bit. I just wanted to show you this one. This one is cool. It's an example of an exothermic process. So all that's going on here is a flame test. It looks like it's lithium, calcium, maybe copper. I'm not sure what that is, maybe potassium. But this reaction is releasing energy. So in this case, the reaction is the system, and the surroundings is everything else. So energy is going from the system to the surroundings. Now, one thing we have to understand is we, as human beings, we are always part of the surroundings. So from our point of view, this fire is hot. So from our point of view, energy is coming out towards us. But from the system's point of view, it's losing energy. But just remember that you are always part of the surroundings. Okay, I got the animation a little backwards on here apparently, but so some terminology here. Heat energy is the energy that flows from one object to another due to temperature differences. I kind of defined that earlier, but its Q is one thing that will stand for that. And then there's another term, enthalpy, and you can more or less use enthalpy and heat energy interchangeably. Technically, they're not quite the same, but enthalpy, you can think of it as the heat content of a system, and what we'll see most often is delta H, meaning enthalpy change. So when the enthalpy of a system decreases, when the system loses energy, it's a negative value for delta H, and it is going to be positive. Delta H will be positive when the heat energy of a system increases. So, something as simple as hot water cooling down, okay, that has a negative value for delta H because the hot water would be the system, and the hot water is losing energy to the outside world. So from that, delta H is negative. Or that fire that you were just seeing, delta H is negative. From the fire's point of view, it's losing energy. Now again, from our point of view, we are gaining energy. If you put your hands near that hot water, you would feel the heat from that energy that the water is losing. So from our point of view, because we're pointing at the surroundings, the fire feels hot. But from the fire's point of view, it's losing energy. So you always got to remember we take a certain point of view when we're talking about energy changes. The term for something when energy is going from the surroundings to the system, so when the system is gaining energy, that's called an endothermic process, like heat energy into the system. So from the point of view of the system, it's gaining energy, delta H is positive. An exothermic process, heat energy flows from the system to the surroundings, so delta H is negative, so the system is losing energy. To us in the surroundings, this one would, if there was an endothermic reaction, it might feel cold because we're part of the surroundings and we're losing energy. This one, like fire, for instance, exothermic, feels hot to us as part of the surroundings. Here's another cool little reaction. This is called, this is nitrocellulose, sometimes called gun cotton, but just an example of a really fast exothermic reaction. As the fire is placed up near the gun cotton, it very quickly combusts, so the system loses energy. We, as part of the surroundings, take in that energy in terms of light and heat in a very quick flash. And so I wanted to show you these real reactions instead of sometimes, I throw in silly little cat GIFs and stuff like that. I thought maybe stop messing around and show actually real chemistry content GIFs. No more silly cat things, except this one maybe. Because it's funny to see cats scared by lizards. There's another lizard right over there that, I don't know, maybe you didn't see the second one coming or something. Oh, I guess he's watching the first lizard. All right. Well, there you go. So some more terminology. Calorimetry is, it's the act, if you can sort of break down this word, metry kind of means measurement, so this calor means heat, so we're measuring the amount of heat energy gained or lost during a chemical reaction or other process. So we're going to be talking a ton about calorimetry. We're going to be doing some calorimetry. You're going to need to learn some calorimetry techniques, all that kind of stuff. Ways that we can try to track heat energy change. Another term, the heat capacity, which is the amount of energy required to raise the temperature of a sample of a substance by 1 degree Celsius or 1 degree Kelvin. The units typically are joule per degree Kelvin, or I shouldn't say degree Kelvin, joule per Kelvin or joule per degree Celsius. Technically, it's not degrees Kelvin. One thing that it doesn't, since a degree Kelvin and a degree Celsius are the same amount of change, at the end of the day, it really doesn't matter whether you use Kelvin or Celsius. If something's temperature goes up by 5 degrees, whether it's Celsius or Kelvin, that's the same amount of change. Now, that's not true of Fahrenheit. 5 degrees Fahrenheit is different, so that's why it doesn't really matter whether it's joule per degree Kelvin or joule per degree Celsius. It doesn't make any difference. Another thing, oh, by the way, notice this is a capital C here. Here's another fun little capital C lowercase key difference. Another thing that's closely related to heat capacity but slightly different is the specific heat. The amount of energy in joules required to raise the temperature of 1 gram of a substance by 1 degree Celsius. So units typically joule per gram degree Kelvin or joule per gram degree Celsius. Again, it doesn't really matter. But really the only difference between heat capacity and specific heat is specific heat breaks it down on a per gram basis. Whereas heat capacity is just the amount of heat capacity of a given sample of something. More or less, the specific heat combines it. Well, I'll get to that in a second about what it combines. It's better when we see the equation. Okay, but let's think about this. Let's ponder this a little bit. What do you suppose has a higher specific heat, water or copper metal? In other words, let's say they were the same mass, so the same mass of copper, same mass of water. I supply them the same amount of energy. Which do you suppose has a higher specific heat? Take a guess. Well, water specific heat is 4.18 joule per gram degree Celsius. Copper is 0.387. So water has a much higher specific heat. So we could supply them with the same amount of energy, and the water's temperature would go up only a little bit, but the copper's temperature would go up a lot, given the same amount of energy. Let me give you an example. Imagine a copper pot sitting on a burner. So there's water in the pot. And if you stuck your hand through the water in the pot and touched the bottom of the copper pan and turned on the heat, you would find that the copper was too hot to touch within a matter of a few seconds. However, if you raised your hand out and maybe just barely touched the surface of the water, you'd find it take, several minutes probably before the water was too hot to touch, even though they're getting the same amount of energy from the burner. So water has a very high specific heat, and it is just difficult to change the temperature of water. So here's some equations that you need. You are given them in the data booklet, or at least I think you're given this one. So you don't necessarily need to outright memorize them, but you definitely want to have them handy. Q equals heat capacity times change in temperature. Delta means change in, or Q equals change in temperature times mass times specific heat. Basically, what heat capacity does is it combines these two terms into the same thing, as we'll see in an example here. But Q is heat, change in temperature, and when you do change in temperature or change in anything, you always have to do final minus initial, so TF minus TI. Little c, specific heat, big C, heat capacity, M is mass. You're going to get answers of a certain sign. It's important not to mess that sign up. If you get a negative answer, that means it's exothermic. The system is losing energy. If you get a positive answer, it's endothermic. So a pretty easy equation to use, at least when you do basic problems with it. Now, I wouldn't write this problem down. We've got plenty of practice in the workbook, but maybe you could just kind of watch a second to see how it goes. Okay, so just watch me, and you'll have a chance to practice here in just a second. But one thing I'm noticing about this problem is it does give me a specific heat. It seems like I could use it. So the equation here is mass times specific heat times delta T. There's a few different ways you could do it, but why don't we go ahead and find that delta T first. And to do delta T, we have to do TF minus TI. We must do it in that order. So the change in temperature of this object, it went from 45.5 to 68.9, so it's heating up. So its final temperature is 68.9, and its initial temperature is 45.5, and we subtract those two things, we get 23.4 degrees Celsius. Now, like I said, it doesn't matter whether you use Celsius or Kelvin. If I changed this to Kelvin by adding 273, and then I changed this to Kelvin by adding 273, and then I subtracted them, I would still get 23.4. So it makes no difference whether you use Celsius or Kelvin in this particular instance. So pretty simple and straightforward application of the formula here. Just plug things in. We get 25.0 grams times 0.257. Now I'd urge you, as always, now I'm going to write my unit like that instead of the negative subscript thingies there. I would urge you, as always, to pay attention to your units and make sure that your units are canceling out properly. My delta T is 23.4. Sorry, that's a little bit hard to see there, but my grams are going to cancel here. My degrees Celsius are going to cancel here. It's going to give me an answer in joules, and that's good. I guess this doesn't ask me for a specific energy unit, but a lot of times it will. And joule is just fine. So when we multiply these things together, we get 150.3 something joules, but 3 significant figures is what we want. So 150 with a decimal at the end would work, or you could write it in scientific notation. And it is positive. The system is gaining energy because it's warming up. So the fact that we get a positive answer there makes sense. Let's try this next one. And again, don't write down this problem, just watch me solve it and you'll have a chance to practice. So it says 100 grams of water has a heat capacity of 418 joule per degree Kelvin. When energy change occurs and the temperature of this water changes from 35 to 30. Okay, so one thing I'm noticing is it's giving me a heat capacity. The equation I showed you said Q equals heat capacity times the temperature change, either degrees Kelvin or degrees Celsius. This 100 grams here is kind of a little bit of extra information that you don't actually need, because the heat capacity is accounting for this mass of water here. So I do need to find the delta T though. I guess this should be delta T here, sorry, that it's going to be in Kelvin. I do need to find this delta T. It has to be TF minus TI. And the final temperature is 30 degrees Celsius, and the initial temperature is 35 degrees Celsius. So therefore, my delta T is 5.0 degrees Celsius. I'm subtracting, so I should round to one digit past the decimal here. So that is the correct sig figs. Now all I need to do, and again, this is why we need to watch our units, we need to pay attention to our units. And by the way, this also is the same as 5 degrees Kelvin or 5 Kelvin. It doesn't make any difference like we talked about. So all I need to do is multiply my heat capacity, which is 418. Now look at my units, joules per Kelvin, times my temperature change in Kelvin, which is 5. So if I just multiply these two things together, then I will have it. So multiplying these two things, we get 2090 joules. Degree Kelvins cancel. There's no extra information there, so everything is working out nicely. Like I said, I didn't end up needing the 100 grams. That's our answer. Sig figs are good because this has 3 sig figs. Oh, actually, we should probably have 2 sig figs, which we'd have to write in scientific notation. So that would be 2.1 times 10 to the 1, 2, 3. So if we want to get technical and have the correct sig figs, we'd have to write it that way because of this 5 Kelvin right here. All right, folks. Thanks for watching. Hope you enjoyed yourself, and we will see you next time.